Hey, what's up guys, I'm Mayank Singh Chauhan and welcome to my introduction on the Rabin-Karp algorithm. Well, Rabin-Karp was developed to solve the problem of string matching. String matching is when you have a piece of text and you want to search for a particular pattern in it. Well, as I said, string matching involves finding all occurrences of a given pattern in a text string. Use cases, if I press Ctrl plus F here and type in string matching, well, this is an example of one string matching. In bioinformatics, it is used in DNA sequencing. Search engines use it, and also it is used in plagiarism detection softwares. Well, let's have a look at some of the terminologies and then we'll look at how we have actually solved the problem. Well, first of all, the pattern is the thing that you want to find in the text. Well, we denote the pattern by this capital letter P and then the indices 1 to m. The length of the pattern is m. The text is represented by the letter T, a capital T, and then the indices 1 to n. Both draw characters from the finite alphabet sigma. We say that P occurs with a valid shift S in T if the pattern is equal to the text shifted with S characters. So let's say the value of pattern was ABC and the text was DABC. So for S equal to 1, this would be a valid shift. The string matching problem is the problem of finding all valid shifts in which a given pattern P occurs in a given text T. As simple as that. Well, the most intuitive approach to solve this is this algorithm, which is derived from the book Introduction to Algorithms, 3rd edition. We save the length of T in n and length of P in m as we usually denote. Now we let S range from 0 to n minus m. That is, we let S take all the values of shifts it can take. And then we compare the pattern to each substring of the text T. And if they match, we say pattern occurs with shift S. What could be the complexity of this algorithm? Well, S ranges from 0 to n minus m, and to check for equality, we need to check equality of each character, so it takes order m time here. So order m into n minus m, we can say that. Well, we usually add a plus 1 here, and that's because say n was equal to m, and if this plus 1 hadn't been here, this would become order 0. Well, that doesn't look something nice, so we write it as order, say theta n minus m plus 1 into m, because this is an exact tight bound. This method ignores the information contained for one value of S when we are looking for another value. Well, what I mean by this is that, say for value of S naught, we are comparing P with this thing, and the last letter in T contains, say, Z, which doesn't occur in this pattern P at all. In this case, it is useless to check for equality of the next few values of S, because the last character would keep appearing in this text. So such information is ignored by this algorithm. Let's see what Rabin-Karps do. Well, Rabin-Karps has to do some pre-processing. Well, it does a pre-processing of which takes a theta m time. We'll see what it is in a while. Worst case complexity of Rabin-Karp is same as the naive approach, but under certain conditions, it generally gives a good result. There are two basic ideas that people use in Rabin-Karps. First of them is equivalence of two numbers modulo a third number, and the second one is the Horner's rule. We'll come to it later. Let me try to give an overview of Rabin-Karp. Consider sigma to be the set of digits 0 to 9. Note that there is a 1-1 bijection between a string formed from these characters and the equivalent decimal digit number. So for example, the string formed by the characters 3210 is equivalent to the decimal number 3210. That's what this statement means. So the pattern P1 to m is also equivalent to some decimal number which we label as P. Let TS stand for the decimal equivalent of the substring of the text which is shifted with S characters. So this is what TS is. Well, it is basically clear that S is a valid shift if and only if TS equal to P, for when TS is actually P, the number represented by TS is same as the number represented by P. Well, that basically means that the string represented by TS is same as the string represented by P, and that's what matching is about. Let me try to make that clear with an example. Say that text T consists of this string, and we'll have to look for this pattern in this T. These two are basically strings. Now we'll generate these values P, T0, T1, T2, T3, T4 till T7. P is 456, as simple as that. T0 is equal to these three numbers, 123. T1 is 234, T2 is 345, and similarly until T7, which is 456. Now what we'll do is that we'll look for matches between P and these TIs. We know that P here matches with T3 and T7. So 3 and 7 are those shifts that we are looking for. Let's slowly try to formalize this algorithm and how actually we go on and do stuff. Well, if we can compute P in theta m time, and we can actually do that using Horner's rule. Just look at this expression of P. If you look at it closely and expand these brackets, you'll realize that we have written PM here, or the units digit number, plus 10 times the tens digit number, plus 10 into 10, that is 100 times the 100 digit number, and similarly 10 raised to the power m minus 1 times PM. So this is really the decimal equivalent of the string P1 till PM. And this can actually be done in theta m time, because we'll start with P1, we'll multiply 10 and add P2. To this value sum, we'll multiply 10 and add P3. Then again to this value sum, we'll multiply 10 and add the next one, that is P4. And we'll continue this loop until we hit M. So M iterations for this loop, theta m time, we got P here. In a very similar way, we'll compute T0. And this is the pre-processing that we need to do. Once we have done this, we can easily calculate the remaining TS using this recursive equation in theta n minus m time. What we do here is that we take TS and subtract the last digit of the original TS plus 1 thing, multiply it with 10 to create a space for 0 at the end, and then we basically add the units digit of TS plus 1. And we do this for each S so that we get T1, T2, T3 until the end. And this can be done in theta n minus m times, because this whole operation is basically order 1. Well, we can actually compute 10 raised to the power m minus 1 previously and then use it again and again. And all this arithmetic is basically simple calculation. For now, we are assuming that these numbers are not large enough and their calculation doesn't depend on their size. So let me go over what I did. First we get P and T0. This is the part of pre-processing that can be done in theta m time. Then we run the actual algorithm in theta n minus m time, or as I said, we can write theta n minus m plus 1 and calculate T1, T2 until Tn minus m. Thus, with theta m pre-processing and theta n minus m plus 1 matching, we found all the candidate shifts. That's true because only those values of S are good enough for us, for which P is equal to TS. I mean, after doing all this, we'll get a lot of values of TIs, which will range from T0, T1, T2 until Tn minus m. And we'll match P with each one of them. And for all those S for which TS is equal to P, we'll say that those values of S are the candidate shifts. Say if there are R candidate matches, now we'll compare each one of them to P1 to M, and each match takes theta m time, and this will take a total theta rm time. You may ask, what is the need to match them once more? Well, that is something that we'll head on to in the later slides. In the worst case, there can be n minus m plus 1 matches. If R is n minus m plus 1, this algorithm would have taken a time of theta n minus m plus 1 into m, which is exactly the same as what the naive approach took. Well, there is one problem in this algorithm that we had overlooked, and that is the problem with large numbers. Well, as we said that T stands for text and P is a pattern that we have to find. P can be really big at times. P and TS have the same size. So if P and TS become too large, then we may have problems with the arithmetic. For this reason, we do all arithmetic in modulo Q domain. As in, we write TS plus 1 equals this blah 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 mod Q. And here also, originally we had 10 raised to the power m minus 1. But now, we will be writing 10 raised to the power m minus 1 mod Q. Well, this guarantees that all TIs will be less than Q. And that's important because now we have small numbers. We have a way to limit the size of numbers. The modulo Q is chosen as a prime number such that 10Q just fits within one computer word. A computer word is way how the memory computer is assigned. So, not more on that, just know that Q is chosen in this fashion. Well, let me go over all this once again with an example. So, let's say this whole was a text string and we've chosen the value of Q as 13 and then we'll try to solve for T6. T6 means the value of shift is 6, so as we begin with 0 here, T0, T1, T2, T3, T4, T5, T6 starts from here. Since only 5 letters are highlighted here, it must mean that the value of M should be 5, and if you divide this number with 13 and find the remainder, it gives the value of 7. This is how we solve for TS plus 1 given the knowledge of TS. So T6 we calculated as 7 here. To solve for TS plus 1 or this part of the number, this number can be written as the original number minus 3 multiplied by 10 raised to the power m minus 1 into 10 plus 2, and then we take the mod with 13. The mod with 13 propagates inside this 31415 mod 13. We calculated 7 in the previous case, minus 3 into the mod taken of 1000 with 13, which is 3. We multiply it with 10 and add 2 mod 13, and this gives 8. So we calculated T7 as 8. So let's say we did this for the whole text and ended up getting 7 twice. Well, let's say the pattern was also 31415 and this one mod 13 gives us 7. So we see that there have been two candidate matches, one here and one here. Now this is why we said that we need to compare the pattern with the valid matches, because there can be some false positives, just like this one here. Now the number 67399 when divided by 13 also gives the remainder 7. But this doesn't mean that this has been a valid match. So for all the candidates that we get, we need to compare the value of pattern to the string itself. Hence, on comparing 31415 with this one, we say that this has been valid. But when we compare 31415 with this number, that becomes a spurious hit. Let's have one formal look at the algorithm itself. So we'll start with defining N and M as the lengths of T and P respectively. We say D is the arity of the alphabet set. Consider it to be 10 in our example, and that will help you understand the algorithm better. We save D to the power m minus 1 mod Q in the value of H, and then we initialize T and P0 with 0. This is part of pre-processing where we calculate P and T0 using these two simple equations that we did over past few slides back. Then finally we let range S from 0 to n minus m. If for any value of S the TS becomes equal to P, that is S seems to be a candidate match, we compare the pattern with the shifted T, and if they are equal, we say print pattern occurs with shift S. And for values of S less than n minus m, we need to compare the next value of T is, right? So we write TS plus 1 equals this thing as we few slides back. But let's see, why is this algorithm better than the naive approach? Well, in most cases, we expect a constant number of matches, say C. Time complexity in such cases is n minus m plus 1, which comes from the fact that we calculate TIs again and again, plus C times m. Well, this C comes because there can be a max of C matches. So for all the candidate matches, we'll compare the pattern with the substring itself, which will take order m time, and we'll do it a maximum of C times, so Cm, and this can be written as order m plus m. Rabin-Karp is not the end. There have been some other algorithms developed, like the finite automation and the Nuth-Morris-Pratt algorithm. They have their own preprocessing, they take their time, and for the matching they take order n, unlike the naive and the Rabin-Karp. The naive is the only approach which does no preprocessing and just starts off with the most intuitive approach. I'm afraid we've come at the end of our presentation. This is me, Mayank Singh, signing off. Thank you for watching.